The goal is to build an AI system that is smarter than humans at physics. We offer one product and two services around the materials discovery side. We really want to focus on these materials that will change and affect all 8 billion lives.
Hey everybody, welcome back to First Principles. We are here today with Deep Prasad, who is the CEO and founder of GenMat, who is a really uniquely fascinating company, and I think maybe the perfect company for First Principles, because there are so many places that we could take this conversation. The company, I'll let Deep describe what the company is actually building, but just to give you a glimpse, it's going to be everything from material science to AI to quantum computing. There's literally anywhere that we could take this conversation, even literally space, which, you'll find out how that's possible in just a second. So, Deep, thank you so much for joining. I'm really happy to have you. Why don't you tell us who you are and what you're building?
Yeah, thank you so much, Christian. Pleasure to be here, and it's always a fun time chatting with you. And I'm, looking forward to talking about what we're doing at GenMat. So, a quick little breakdown on GenMat. Our goal is very simply stated, but very hard to do. The goal is to build an AI system that is smarter than humans at physics. That's it. So how do we, basically create something that can, let's say, discover the next generation of physics theories that advance what we did with quantum mechanics and general relativity in the early 1900s? How do we build really advanced physics simulation systems, right, that can essentially simulate these very hard regimes like the hypersonic regimes and, atomic oxidative environments in space, for example, which require a lot of multiple different physics modeling techniques. And so at GenMat, we work on the sort of intersection of physics and machine learning or artificial intelligence.
That's a perfect intro. So basically you're building a physics understanding AI, like an AI that knows the laws of the universe and basically can tell you what to expect if you give it inputs and then something comes out the other end, basically, right?
That's exactly it.
I think it's fascinating to think that AI wouldn't just naturally know that, right? So AI is super smart. AI is now over 100 IQ. So why is it difficult to just program in just F equals MA and E equals MC squared? I don't know. I'm obviously just throwing you a little softball, but why is it so hard?
It used to be a very philosophical question before we made so many advancements in these large world models, before we could actually figure out how far can we push, silicon transistor-based, let's say, large language models and their understanding of the physical world. And so the reason why it's so hard is, A, because we have embodiment. But let me take a step back before I go deeper into that. Embodiment kind of covers three parts of human intelligence, if you will. The general intelligence that actually affects our ability to understand the physical world. And those three sort of components that I think separate us from, let's say, my dog, right, who's obviously brilliant in her own way, but certainly not making rockets or, working with satellites anytime soon like you are. So, our team is. The difference is that humans have these three components, which is the sensory apparatus. Up to 50% of our brain can be dedicated towards visual processing of information. So it's not that our eyes are, as good as a hawk, right? But it's the signal processing that we do, the computational processing, that makes it powerful. And then there's the second component, which is our ability to imagine, or creativity, the ability, more precisely, to simulate physical systems that have yet to be tampered with. So take, for example, Einstein's thought experiments when he was discovering relativity, right? This guy's literally thinking about trains and lightning and then using that to derive special, right, general relativity principles. Or dreaming how one does as they traverse through the universe as a photon. All of these things require the ability to simulate physical systems, and that to manage and store in memory abstract concepts. And these representations of the world that are physically accurate and useful is what's so hard to do even now. Today's large language models don't come close, actually, when you come to think about it. And then the third component between sensing simulation is the engineering and manipulation of matter. So when you have a system that's capable of sensing of simulating the physical world and manipulating the physical world, you should have something as smart as a human or smarter. But because today's large language models don't have any of those things in a really cohesive framework, we haven't really been able to crack, just F equals ma. A four-year-old child, for example, will know more about physics, to Jan LeCun's point, right? Than like ChatGPT 4 does, or 5 or 6. Why? Because when that child, let's say, jumps from 4 or 5 foot like tall ledge, like something really freaking high, right, for the kid. Like imagine when we did that when we were young, right, and we were troublemakers. What would we do? Well, you would jump from a high place and you bend your knees, right? And why do you bend your knees? Because the equation for power is energy dissipated over time divided by time. So if you can increase the denominator, the amount of time, right, you're reducing the amount of power or shock that your body is experiencing. So we don't have these explicit equations that our brain is solving when we jump. Our muscle memories and cells and neurons that compute have learned the right sort of representations of physics, and so all that is missing today.
So it's the sensing, the simulation, and the manipulation of matter. Those are the three things. I mean, intuitively to me, AIs or computers in general are pretty good at those things, right? Like sensing, we can definitely make cameras that are better than my eyes, and for simulation, we have Monte Carlo sims that can run millions of possible futures, and my puny brain could never handle that. So I don't know, it seems to me that why aren't computers better at those things today?
They're not better at those things today because they're not integrated like we are. So we're an integrated sensing, simulation, and manipulation of matter system. However, if you take let's say, sensor in a Tesla FSD, right? What's stopping that FSD from visualizing the warping of space-time under different metric tensors? It doesn't have the physics simulation-based models, right, to do those things. But those are the things that we work on. So hopefully one day in theory, right, maybe your Tesla can think about relativity because of us. And so the other part is the manipulation matter. So, the Tesla in this case is moving around, you're trusting it, but it's not going to go and build an arc reactor in somewhere in a cave, right, to go and test its physics theories that I can't think of right now. So the difference is the integration. And so our brain has had, right, billions of years to really integrate all these systems and evolve the integration of the systems. So that's the edge we have currently, but we'll see how long that lasts.
Presumably, the fundamental constraint here is sort of twofold. There's one is finding ways to represent the laws of physics to a computer in a way that a computer can understand it. I mean, I'm sure at some point you do literally plug in F equals ma or E equals mc squared or something. That's probably part one. And then part two, I would assume, is just you have to get a ton of data. You have to feed in, I don't know, what happens when you drop a ball, or what happens when you jump off something. You probably have to feed in examples of physics. And so I wonder, what did that even look like? What does physics data look like, and how do you capture it and feed it in? So I don't know. We could take those two halves in either way, but I'm curious about both.
I'd love to, look at what the physics data looks like and the difficulties there. So, and really it's a combination of both. So our equivalent of, F equals ma of dropping a ball and seeing, how many times will it bounce given the friction coefficients and so on, is we started with the atomic world first. There's a reason for that, and I can get into it if you like at any time. But we wanted to build our world models, our physical world models into our AI systems, truly from the ground up, from base reality up, because that's the best way to predict everything else, right, is if you can model the underlying crazy atomic world, since that dictates everything. And so for us, that data of what does a different basketball under different scenarios look like? A real life example of that is our titanium dioxide photocatalyst system. So we recently put out a preprint, for example, where we created the following setup. We have this titanium dioxide nanoparticle. They're 10 to 25 nanometers across. And on top of those nanoparticles, we deposit copper and platinum nanoparticles or nanoclusters. And these sort of nanoparticles are just globs, right? If you want to think about them, they're amorphous globs of copper and platinum. And the way that their configurations end up completely dictate where the photocatalytic activity will be. And the photocatalytic activity is what we care about, because this system absorbs carbon dioxide, absorbs water and sunlight, and turns it directly into natural gas in a very clean reaction. There's no waste products. All you get is literally methane out at the other end of it. So what we've done over the past few years is taken this system and we've looked at optimizing the nanoparticles and determining what configuration of the copper and platinum atoms would be most conducive for sucking in more CO2, basically. How do you accelerate that? And so traversing that search space, combinatorial search space of configurations, goes up in a very quickly, exponentially, essentially, and factorially, when you take into account that you have 3 dimensions. So one sort of, just take the nanoparticle system that's sitting on top of the TiO2, right? So there's a combinatorial system where the copper and platinum atoms have different permutations that they can be in. And the more of those atoms you introduce, the more different configurations they can all fall under. And on top of that, you can introduce different oxygen vacancies on the surface of the TiO2. When you pluck out the oxygen atoms on the surface of the TiO2, you also change the catalytic activity and what's happening at the interface. And the interface between the TiO2 and the nanoparticle now is this really rich area of super complex chemical activity that you can optimize to do something useful. And so it's being able to model those things, creating data sets that represents all these different systems from first principles, and then validating our predictions in the labs is where we started. And then over the past year and a half, we expanded into geophysics, which is where our satellite work comes in.
Yeah, wow. Okay, now I'm definitely convinced that computers are way better than me at this. I got a little bit of that, a little bit, but I mean, what I take away from that is basically you are trying to super detailed and in a lot of granularity model literal atomic level activity. You're saying like, what happens when you put titanium oxides, like titanium and oxygen, together with copper globs? Like what ways can the globs be oriented? And if they are oriented in different ways, did the material have different properties?
Time you change something, you change the material properties, by the way. So good luck doing that for millions and billions just for a tiny small material.
You're simulating to try to figure out which things are worthy of test.
You got it.
And then once you have like a candidate list of stuff, then you go and like test it and actually like measure the material properties. Is that basically how it works?
There you go. That's exactly the process.
Wow.
Rinse and repeat.
So how does it work today? Like if I'm a material scientist today and I'm trying to like come up with the next room temperature superconductor, like what do I actually do if I don't have a physics AI like this?
Yeah, absolutely. So right now it's very much trial and error. Literally, you're mixing shit. That's it. It sounds super complicated, describes synthesis and characterization, but it's just a bunch of dudes in a lab, right, and girls and so on, just mixing different chemicals and solvents to synthesize different compounds. And they're doing it based off of decades of experience and intuition and very, very, very slow, archaic computational chemistry tools that are written in Fortran. So that's the art, right, of material science today. And that's what powers the semiconductor industry, the aerospace industry, the battery industry. All these industries are bottlenecked by this current process.
I know about the discovery of some materials. Like I know that, I don't know, like back when we discovered bronze, like it was literally just a mistake. Like someone accidentally dropped some iron or something in copper and then it's like, oh shit, this is actually harder. Like this is actually better. And like this happened it happened with like penicillin. Like, I don't know, there's like rubber. I think that's literally how vulcanized rubber was made. Like it was like an accident. Like, so it makes sense. It makes sense that, it's like people are just making mistakes in labs and then every once in a while it turns out this super material. So it's crazy that that's as good as we've got.
Yeah, absolutely. In fact, even when you have, let's say, experts with some intuition of what they're doing, like some idea of what they're doing, right? It's not just a straight up lab accident that they're banking on, like perhaps a potential alkali-9, right? Submitters were. Even then, it takes a decade or many decades to drive the materials. So if you take the first high temperature superconductor that was discovered, what's awesome is that was discovered by a private company, IBM, right? That was discovered by IBM scientists. And when they discovered it, there's a lot of history to that. So it was the world's first cuprates, right? These copper-based, essentially ceramic-based superconducting materials, which in itself was a profound sort of discovery, right? That, oh wow, you no longer need just a metal or perfect conductor or normal conductor to become a perfect conductor. can literally just be this weird material, right? And so that wasn't by accident, however. So Bednarz and Mueller had spent the past sort of decade, particularly Mueller, really just focusing on the crystal structure of what would be expected, right, of these cuprates and of high temperature superconductivity. So they were looking at all these other crystal structures that were precursors to the final cuprate crystal structure, the arrangement of atoms that's like essentially a fingerprint for that particular material. So that family of fingerprints they had been looking at for so long. And so finally they like stumbled upon this, but that's what they were looking for, right? And it was because of one of the key ingredients, funnily enough, was access to some of the first like really large-scale density functional theory, large-scale for their time in the 80s and late 70s. So that's pretty awesome too, right? It's a combination of computational chemistry and real experiment and maverick science coming together in a private industry setup. So we should be trying to do that again.
Today's episode is brought to you by NordVPN. Now, there are lots of reasons why you'd want to preserve your privacy and secure your online browsing. There's the normal reasons like not wanting to get hacked, which is pretty essential for deep tech companies like the ones featured on this show. But there are also some other ways that VPNs help you that are less known. Like you can get deals that are only available in certain countries, and you can get access to shows and other media that are, again, country specific. And if you're going to get a VPN, use NordVPN. They're the fastest on the market today. To get the best discount on your NordVPN plan, go to nordvpn.com/firstprinciple. So you'll add on 4 extra months to a 2-year plan. And there's no risk. There's a 30-day money-back guarantee. So check out that link, which is in the description of this episode, or go to nordvpn.com/firstprinciples. Let's get back to the show. So maybe let's take a step back and just talk about materials. Like, what is material science and what are the properties of materials? Like, I imagine what you're searching for are specific properties. Like you want to find materials that are really conductive or like superconductive. You want to find materials that are extremely hard. You want to find materials that are whatever, like a variety of different things. So do you mind just telling us at a super high level, like what are materials and why do they matter and what makes them good or bad?
Happily. I love that question. So materials were just arrangements of atoms that repeat at a scale that's relevant to you. That's how I would define it. So you don't care about like 3, 4, or 5 groups of atoms, right? Or like 5 atoms. But you care if you have trillions of atoms that intricately dance with each other and represent the next generation of semiconductors, right? That are more power efficient. You care when it's carrying you to the moon and to Mars. That's when it matters. So that's what I would define a material. And so you can have many, many different kinds of material properties that you're interested in, right? All the way from conductive properties, like you were mentioning, like electrical properties, thermodynamic properties, structural properties. Those are really common as well, right? So within those, you have a very wide range of sort of trade-offs. Every material has its own trade-offs for its properties. So for example, you might be interested in looking for a transparent solar cell, like a truly invisible solar cell. We're about 70% of the way there last time I checked, where like we can create about 70%, right, translucent solar cells. That field of research is largely being enabled by Perovskites, which in itself is a fascinating material, right? So in material science, let's go back to the like 30s and 40s when Perovskites were first discovered. There are these interesting rocks with these interesting piezoelectric, electric qualities to them, right? People go around rubbing them together and seeing that they create charge if you hit them against each other. And they're like finding other rocks like that. And then we find out that about 70% of the Earth's crust, or a very, very large percentage, has these perovskite materials. It's largely composed of perovskites all the way down, not instead of turtles. And so in the 1960s, we have about 60 research papers, let's just say, per year on the subject of perovskites. And I'll tell you what they are in a second. And now today, we easily have 80 to 100 research papers published per day in that field. It's the most famous, I would say, after superconductors, or even on balance, it really does become the most famous material that people actually put resources towards in practice. And there's a reason for that, because perovskites are these, they have an ABX3, so an anion, and cation,
like configuration, right? So basically, the ABs are anions and the X3 is a cation. And so the anions create this octahedral pattern. When you repeat the atoms, right, and you look at the fingerprints and what they look like at scale, they create these octahedra. And when you tilt the octahedra, meaning when you change the bond lengths, when you change the chemical composition, you tilt the octahedra, or you displace the cation in the center of the cubic lattice, it changes the properties completely. So just displacing the cation, if you want to visualize it, in the center of the cation, and then you have an octahedra covering, right, the cation. So if I axial tilt this octahedra across X, Y, or Z, just one tilt, even a little bit changes the properties. A little bit more changes the properties. How are you possibly predict all those things? But anyways, right, so like, that's why you have so many papers, because it's just straight up surprise. Like, you change it a little bit, it surprises you what the properties are now. So
these materials that are in solar cells, basically, we've known about them forever. Look, what do you mean that they're in all of the Earth's crust? Like, that they're in everything? What does that mean?
Yeah, so there's like magnesium-based perovskites that are largely what I believe Earth's mantle or Earth's crust is.
Oh, okay.
There. So these so that's one example, right? Where it's like literally a large perovskite-based mineral that mostly composes the crust.
Is Perovskite, and that's the name of the shape?
It's the name of the geologist / geophysicist.
And it is in the class of things is like the shape of the thing defines it as if it has that octahedral thing.
The shape of the anions creating the octahedra defines it.
Wow, cool.
And that it's just an infinite, right? Like sort of family of materials that it represents. And so the cool thing is that these near invisible solar cells are based off of the perovskites. The first piezoelectrics were perovskite based and are largely perovskite based. And currently, for example, in our labs, we work with perovskites for lithium-ion based solid-state electrolytes. So how do you find a much safer, much energy-dense lithium-ion battery? So
to kind of tie this back to what you're doing as a company, let's stick on this example. Let's keep talking about this new material. So would a lab come to you and say, hey, I have this idea for what I think we could do with the orientation of the thing, and can you please test it for us? Or like, are you trying to discover your own ones yourself, or maybe both? Like, can you just make it tangible, like what you're doing as a company in relation to all this stuff?
Happily. So we're kind of doing both. We're dog fooding our own products and technologies for what I call ubiquitous materials. So we don't care about creating, let's say, a material for a better, lighter, stronger weight tennis racket, or like a better golf club, right? That don't care if somebody else can commercialize that. We're happy to help them to discover that, right? No problem. For us, we really want to focus on these materials that will change and affect all 8 billion lives. Like, that's our metric. So, for example, what does that look like? A truly 100% or 99% invisible glass panel, right? That's also a solar cell. That's totally up our alley. We're definitely interested in that. A lithium-ion battery, that's, let's say, an order of magnitude safer and more energy dense than what's available in the market that Tesla can deploy. We are happy to help find that and work on that. But then, so we want to kind of do both of these things. And I think that there's a world, right? The world of materials is large enough that there's never going to be enough players making their own materials, making their own supply chains and processes to scale those materials. And so that's why we think that, we just need to keep contributing like crazy to the acceleration of these materials, one way or another, whether it's us or helping other people do it. So our business model is that we offer one product and two services around the materials discovery side. And then I can get into our geophysics-based models, because I mentioned we expanded recently into another domain of physics, right? But so for materials work, we have one product, and that product is a series of physics-informed machine learning models that model crystal structures and chemical compositions. And they're useful for a variety of tasks. We have some models that are really, really good at predicting the properties. So let's say you change, right, these parameters, the axial tilt, the anions, and so on. What can we expect? We have models for that. We also have models that look at what happens when you have a very complex interface, like the titanium dioxide example that I was talking about, where interatomic potentials are very complex and you need to discover or learn a representation for it. And then we have generative models for the inverse design task. So that's for when a customer, and this is what we're finding most people are interested in, is particularly like a much larger market. We also have models for the inverse design task, or capabilities, where you give us target material properties and we will discover, right, and we will figure out and generatively dream up materials that should have those properties.
Are there certain properties that are fundamental enough for you to model, and other properties that are sort of like emergent and you can't model?
Yeah, and when I say can't model, I'll be specific. Can't model with today's physics AI technology. Like, it's constantly active field of research for us to be able to, improve this multi-scales and multi-physics domains that we can get into.
Wow. So what properties can you do today, or what are those fundamental ones?
Yeah, absolutely. So fundamental ones like the band gap, charge density, local density of states, right? Electrical properties like conductivity, both DC and AC, right? We can also model ionic conductivity if you're looking at battery materials. So information energies as well is a really, really critical fundamental property. So yeah, we can model these fundamental properties, which already give you a lot of information about, is this material going to be useful for your particular engineering task at hand? So, let's say you're trying to find like a really efficient solar cell that works really well in atomic, oxygen environments in space. That would be a set of material properties for us, right? Target properties that we would then just like go run our models against. It's one of the directions that we kind of going. We are trying to elevate the aerospace, and space industry while being part of it, of course. Okay, all right, yeah. So those are fundamental properties that apply to a wide variety of materials and material families, from transition metal oxides to, let's say, ceramics, right? You're looking at formation energy and so on and so forth, battery materials, solar cells. You get the point. But there are also emergent properties that you asked about, and I think that's a brilliant question, because there are emergent material properties that require deep quantum computing and quantum computing related technologies and thermodynamic computing related technologies to exist. And so that's what we can't do today. For example, modeling high temperature superconductivity, right, is a unsolved problem because it requires being able to capture really strongly correlated electron systems and many body systems. And it's so computationally tractable, even for the most powerful silicon semiconductors based AI models today. So that's we're constantly pushing up against the physics boundary, if you will, until new hardware comes along.
And so today you're just doing this all with classical computing, or do you use quantum computers today?
We use quantum computers only as a test bed to test how far away is quantum advantage. That's really about it.
I know that you originally, the reason I asked that though is because I know that at one point in time, you and Guillaume, the guy who's the CEO of Extropic, people might know him as Beth Bezos, we did an episode on him a little while back. I know that you guys knew each other back in your university days, and you were interested at the time in quantum deep learning. So was there a time when you were founding this company that you thought it was going to be a quantum company and then it ended up just being classical? Or is it just someday you really hope we're eventually going to get to quantum and it's just not now?
Joe and I, we both determined, right, that, okay, quantum hardware right now, not going to make it for quantum chemistry tasks. So one of the things he worked on even now, currently, the world's most powerful quantum computing simulator, right, based on benchmarks. So he built that at Google X in the secret division that we built. And so that was really a lot of that. Some of that was born, right, out of this acknowledgement that him and I had on the sort of limitations of being able to do quantum chemistry tasks today. That simulator, even today, in the concept of using simulators and decomposing problems across simulators, remains active field of research that we're pursuing, where we've recently been able to perform certain simulations, certain material properties that we can calculate thousands of times faster on this using classical hardware, but using an entirely different paradigm of quantum probabilistic algorithms. And so those quantum probabilistic algorithms will natively work on quantum computers once they come online. That's one of the benefits of writing code like this,
is that you're already getting benefits from this quantum computing simulator that's giving you useful chemistry calculations. And on top of that, you're ready so that when the hardware comes along, it's literally almost a back-end switch, right? Like you're just swapping the device driver to a quantum computing device. Now, that's one aspect of our strategy. But the other part, this is the part that, I'll probably only say a few times, I don't know, just because it brings a lot of heat by saying it. But we are also deeply interested in accelerating quantum computing. I'm no longer interested in being an observer. A large part of quantum computing is material science-based, like constraints. And so hope to say more about that at some point.
We talked about kind of the problem, like how you're approaching it, why it's important to solve, but we haven't yet talked about why AI is the right tool. So I'm curious, like why, when you were trying to do this cool material science discovery, why'd you choose AI?
So the reason why I chose AI is because it's ultimately one of the best pattern recognition, if not the best pattern recognition device we've ever created. That's really all it comes down to. Nature has really, really deep, complex, hard to penetrate patterns that show up between all of these crystal structures, between all the electrons and their bond links and the properties. There are patterns that are meaningful in mathematical and chemical and physical nature. And so teaching a super intelligence that, I think we have a higher probability of succeeding than leaving it to just our wetware. Can
you talk more about the specific techniques that you're using? Is it like, a particular, is it deep learning? Is it some other thing? What of AI are you using to help solve this problem?
Yeah, absolutely. So we use two things. 99% or 95%, if you will, is classical deep learning. So these are for example, we use something called CDVAEs. So crystal diffusion variational autoencoders. This is one class of models that's really interesting to us, right? There's some open source CDVAE out there, for example, that you can play with and see exactly what we mean. So that's taking the best of diffusion-based methods and variational autoencoder methods, and you're applying it to crystal structures.
I know what neither of those things are, so it's that's 0% helpful to me. Let's talk about it though. Let's get into it. So what is let's set a goal of Christian has to understand what a CDVAE is by the end of 5 minutes. So how would you describe what a diffusion model is, what a variational autoencoder is? Let's break it down.
All right, let's start with the variational autoencoder first, the VAE, right? So a VAE takes as some input, learns a compressed latent representation of that learned input, and then it has a decoder, right? So the autoencoder is encoding the input into some latent compressed representation, and the decoder has to get really, really good at taking that latent compression and decompressing it back to the original input, right? And so the autoencoder has to get really, really efficient at compressing different inputs into smaller and more useful and more information-rich latent representations of the input.
And latent meaning in this case that it's not like a literal one-to-one, I see red, therefore I put red in a database somewhere. It's latent meaning that it's just some number and kind of inscrutable. Like those middle steps would make no sense to us.
Right, bingo. That's exactly it. So for example, it's like when you don't want to see in your occipital cortex as visual data gets processed, right? It would look really, if you could see that, it would be almost psychedelic, right? You would see instead of, two eyes for deep, right? It would be two globs that
yeah, totally.
Features. You would just be...
Yeah, if you could peer into the brain and look at what neurons are doing or something like that. It's if you looked at neuron signals, it would make no sense, but it processes it. So it's the middle step between the processing. Okay, so a VAE takes inputs or whatever, turns them into crazy gibberish, but then there's another part of the other side that can take that crazy gibberish and turn it into meaningful stuff again.
Bingo, exactly. So that way, when you give the VAE a totally new input it's never seen before, right? It should be able to compress it in a meaningful and useful way, and then the decoder can meaningfully decompress it, right? And you can make predictions at the ends and beginnings of both of this process. So, for example, with the VAE, right, you're feeding it in crystal structures. By crystal structures, I literally just mean atomic coordinates of materials. They're fingerprints, right? Where are all the electrons and the atoms, the neutrons and so on, particularly in the bond lengths. That's it. You feed those in along with the properties, because each one has different lists of properties, right? so that now you're learning a compressed version of those crystal structures and their associated properties, so that when I give my VAE a new crystal structure that it's never seen before, it should be able to come up with a useful compression, right, that allows me to deconstruct the entire input, including the properties, as an example. So that's the magic of the VAE. Now, what does a diffusion model do? A diffusion model is infamously known for incrementally adding noise to a model, and then training a sort of loss function that you can go backwards and start with a very noisy image and come up with a very coherent image. I won't get into like why Gaussian distributions and so on matter. What I will say is that if you can teach a AI to take a very, very noisy image and find and learn a representation of working backwards to the original images, you basically learn a representation of coming up with any coherent image, because you've trained it to come up with coherent images through and through given noise. So if you give it random noise, right, some form of structured noise even, or whatever, sampled noise, the expectation is that it's forced to come up with a realistic reconstruction, a coherent one, and that's what we exploit. But that's also why you never get the same images. Every time you run Midjourney, it'll never be the same, because you're literally just injecting noise into your system. So now you combine the two, and that's how you get one of our models, at least.
What was it? So it's CDVA. What's the C stand for?
A crystal diffusion. So for crystal structure, and V for diffusion, and then for variational auto.
So crystal diffusion, variational autoencoder. It's a thing that you feed it. Presumably, the way that it gets better is you just feed it tons of data in the beginning. You say, here's a billion different crystals, a billion different properties, and then it just learns what to do with those sorts of things. And then on the other end, the diffusion part of it is basically like the equivalent of Midjourney, like where it starts all blurry and then you kind of get the lumps, random lumps, but then it like coagulates into something that actually is meaningful. Like presumably that's what's happening on the diffusion side of the other. Okay. So you are using CDVAEs to do these like material predictions basically, and also that what you call the reverse thing where you're actually like predicting, you're just trying to find materials that meet particular criteria.
And so so the inverse design problem is, given a set of target properties, find me 1,000, right, or 10,000 material candidates with these properties. Which, right, you would have had to hire entire teams of material scientists before to even like get close to one of those 10,000 candidates at some point.
Seems hardest to me is the data part, is getting billions of crystals and somehow loading them into this machine. Like, what does that actually look like in practice?
And I can see why you think that. It is a hard part. So largely there's, I would say, all three things that have come easy to large language models are very, very difficult for large physics models, right? So the difference, for example, data, right? The training data, if you take large language models, the training data is available all over the internet, right? Yeah, you just need a coherent sentence, literally. It just needs to be a complete grammatically accurate sentence, and that's now training data. And then the processing, the representations, transformers do most of that work for you, right? And so there's obviously an active field of research for transformer architectures that impose these like attention mechanisms that are useful for learning, like all these extra subtasks, right, implicitly. And then you have the RLHF. You have thousands of people, hundreds of thousands, millions of people who can RLHF the output, right? And like roast your AI. Like that's pretty easy. Right? But if you have a physics-based AI system, coming up with valid training data is very, very expensive. You need deep domain expertise, labs, lots of compute. So, for example, the data for us is our experimental labs. It's also the synthetic data sets that we create using proprietary know-how methods. It's also first principles computed data that we create, and that's using like these massive DFT softwares. Very archaic software.
What's DFT stand for?
Oh, density functional theory. Sorry.
Density functional theory. Okay.
So density functional theory is a computational modeling tool. It's a approximation to the many-body Schrodinger equation, which every single material has a unique fingerprint. Every fingerprint has an associated many-body Schrodinger equation to it. If you can solve it in its exact form, you would be able to predict
pretty much all the material properties that you're interested in, all the properties. And so the problem is that we can only solve that for about 3 atoms. Beyond that, computationally possible. And so that's where density functional theory was introduced. It's this computational method. So we have these old school software codes, right? Like creating data sets as well in part. So it's just, how do you just create really high quality physics data? In itself is an art and a science. And then, so that's hard, I totally agree. But I would say even the representations are hard too. So how do you impose physics symmetry constraints? For example, if I may have a molecule, let's say, right, of titanium dioxide, and I may rotate that titanium dioxide molecule a few degrees across, like, let's say, the x-axis, x and y plane, right? So I just rotate a little bit. To my neural network, which is my CDVAE, right, this deep learning algorithm, it's only seeing numbers of positions of and electrons. So if I rotate it this way, all the numbers change completely in no known and obvious ways. So it will think, if I don't include physics constraints and symmetry constraints, that is new data that it's seeing a totally new molecule.
If I show my phone like this, then it can see, oh look, it's like a shape like this. But if I show it like that, even though we obviously know it's the same phone, like it looks different because there's different pixels that are like representing all the black squares.
Bingo. That's exactly it. But basically, how do you do 3D object recognition, right? Recognition, but for atoms. So there's difficulties there. So finding the physics symmetries, in this case, you would impose E3 equivariance, right? So it's it comes from like group theory. So group theory is a form of pure mathematics that studies mathematically describing and quantifying symmetries. So you can have symmetries in physics, and you do deeply, right? Like you have energy symmetries and constraints, conservation momentum, and so on and so forth. So yeah, all these things have categories and groups particularly attached to them. So anyways, you have to impose like really, really deep, complex mathematical rules into the neural networks that don't just come out of the box for large language models. And then the third part, the RLHF, you can't just hire a random person who understands English.
Yeah, and that the RLHF stands for reinforcement learning with human feedback, right? Or with human features or something. Is it feedback or features? I never know.
Yeah, you got it right the first time.
Okay. So what that means is basically you show people output number 1 and output number 2, and they say, oh yeah, I prefer output number 1 or something like that. But if you show me this crazy material, like I have no idea what to do with that. Like I don't know how to rate that on a scale of 1 to 10. So that makes sense. So what does that actually look like? What does the reinforcement learning part look like? Is it just doing more measurements after you create some stuff in a lab and testing to see if it was good or bad or right or wrong?
Yeah, that's really what it comes down to, is largely nature herself becomes the arbiter of truth for us. Nature is the feedback for us. It's like NLHF, right? Or sorry, RLNF, right? Reinforcement learning from nature feedback. It's like the simplest way to put it.
So that's like the hard parts. I imagine that your product is very complicated. And for a lot of people that are not detailed, like as expert as you in a lot of these areas, I imagine it's very hard to communicate and like hard to kind of get people the necessary background information they need to understand it. And yet you probably have to hire a bunch of chemists who don't have all the AI background. And you probably have to hire a bunch of AI people who don't have the chemistry background and vice versa. So my question is there any way that you actually do that, like as a company or even just as you, like going out and pitching investors or something? Like how do you try to get people the first principles understanding they need in order to really understand this thing?
I try to communicate it in a way that they can relate to deeply and intimately, right? So like, let's say I'm talking to someone who works construction all day long. That person may not have the same deep technical appreciation of like chemistry as someone with a PhD in chemistry, right? So how do you and that person, the PhD in chemistry, may be a complete novice when it comes to applied materials in the real world, like the construction worker is, who actually understands melting constants and so on and so forth, melting points and real structural integrity, what that actually looks like. So there's knowledge gaps in both places, and so that what keeps them kind of threaded right together is that shared understanding or appreciation, actually more importantly, of materials. So I always take that kind of first principles approach,
And so that's always like been like pretty useful in retrospect. It's just like finding something in their day-to-day lives that matters, and then kind of just showing them the appreciation of like how hard it is to actually find materials like that. A lot of people, I think, just kind of take material science for granted, right? That plastics, leather, silicon, all these things just exist. They don't. They take very, very hardcore labs and a lot of scientists, a lot of time to discover. So yeah, just communicating that, and then communicating the physics as well, right? So like the baby example or the child example of jumping from a high top, everybody understands that. So that's like one example.
Like if you're just looking at your company for the first time from the outside, it does seem like you have you've all these different areas you're trying to do in sort of like all at once, seemingly. Like you're not only doing like materials discovery, but you're also doing materials analysis. You're not just focusing on one material, you're focusing on like all of them. Like you're doing photoelectrics, you're doing like whatever, like conductive stuff, you're doing all these other, like you're doing so many different kinds of things. And so is there a reason you chose to do that? Is there a reason you chose to go really broad instead of just being like the one ceramics lab or something?
But absolutely. That's probably, I laugh because that's like the first question VCs would ask.
Why aren't you focusing?
That is such a common question, right? Where is your focus? I'm like, and my answer is always the same. My focus is the system. We are trying to build an AI that is better at physics than all humans combined. That is the goal. And so that AI can't be trained on just ceramics or just batteries or just geophysics or just computational fluid dynamics. It really has to sample from all sorts of domains of physics and truly be embedded across all different kinds of sensors around the world. So I'm kind of taking that systemic approach. It might look sporadic, but it's like a hypercube, and
we just don't have the us puny VC brains or whatever don't have the ability to visualize cubes in our brains. So
haven't communicated it well enough yet.
Okay, so let's talk about the geophysics stuff, and let's talk about space. Let's get there. So why add another thing? Come on, man, you're not focusing. Like tell us why you want to do it.
Yeah, if disrupting material science wasn't hard enough, like, well, why you yourself would try to disrupt, like, geology, right? But basically, like, the benefit is twofold. In the immediate short term, our short term, right, when I say that, like 10 years or less, right? Massive benefits here is that we're going to be able to help with critical materials and critical minerals supply chain, as well as just a general raw material supply chain, which also benefits us and our customers. As our customers at, let's say, the SpaceXs, Teslas, whatever of the world, right, are prompting our AI to look for new materials, new alloys for their rockets, for example, or engines, and so on. There's going to be net new atomic species or elements, net new as in versions of these raw materials that we typically haven't cared about, right? So pick your poison. I'm going to pick an extreme one like francium. Obviously, it wouldn't pick something like that, but you get the point, right? So there's going to be a sudden increase that we foresee over the next few years in absolutely new supply chains for raw materials that don't exist. And so if we can put up satellites in space and have geophysics-based AI models that reduce the cost of exploration and time for exploration of those new minerals, we reduce the cost of the raw materials themselves. So that's a very kind of like simple first order, if you will, effect that we want to exploit or leverage, if you will. And then the kind of longer term goal that this serves, the geophysics and satellite work, is going back to the original three components that we talked about. So the geophysics satellite work, hyperspectral work, also has a secondary benefit that's more longer term. And that goes back to what we talked about earlier, about the three critical components to general intelligence from our perspective. And so that's the sensing, simulation, and manipulation matter. So the more sensors we have in space, on the ground, underneath the sea, throughout the real world, the better it's going to be for a physics-based AI.
Yeah, makes sense. So basically what you're trying to do is be able to have cameras, like hyperspectral cameras, right? Not just like optical cameras. So a camera that can see every sort of wavelength from the narrow little, like whatever we can see, into the infrared, into the ultraviolet, like just even beyond that probably. So it's like, yeah, it takes all of that visual, call it visual data, and can look for materials. So you say, we know that copper looks like this when it's on the ground. It has this particular pattern, basically. Is that like a simple way of describing what you're doing?
That's the simplest way to describe it. That's right. So we're literally looking for signatures of different minerals. Copper-rich minerals versus iron-rich minerals will have a totally different reflectance pattern underneath the hyperspectral signature. To you and I, it's just going to look like dumb rocks. But to a specialized camera, they're very, very pretty and colorful. And each color is super meaningful in terms of the chemical and crystal structure decomposition of those minerals. And so some deposits, what we want to be able to do is, exactly as you said, point to deposits, right? And point to drill targets. Where should we actually drill and look for these like precious deposits? If you take something like a periphery, the causal relationship between the surface scans and the periphery are a lot stronger. A periphery is a geophysical sort of phenomenon that occurs across millions of years when you have a volcano nearby. Essentially what happens is you have really, really hot magmas kind of circulating and heating up all these hot like metals and precious metals like gold and silver, and it circulates these like really precious metals that we care about across millions of years deep underground, up anywhere from 100 feet to several hundreds and thousands of feet beneath the surface. And so you have kind of like a Eye of Sauron looking thing. and around it are all these, like, it's literally gold and silver. It's like it's a nickel and other things you care about. And then on the surface, it's really, really low grade material, but it's still like a lot of gold, a lot of silver. And so a lot of peripheries have yet to be discovered, by the way. That's the cool part. So there's a lot of surface mines that yet haven't even been detected, and we will see them with the right AI and the right system, I think.
So you actually launched a satellite, though. You launched a hyperspectral satellite on a recent SpaceX launch, on Transporter 9, was it?
You read it, exactly.
Tell us about it. What was that like, man?
Oh, man, that was so nerve-wracking and exciting. It's like easily top like experiences of my life, hands down. That was so cool. Like, you know, like, I'm sure you experienced this too when you were going through your first payload. It was just like, all right, we're putting a lot of money into this thing. There's a lot of hardcore engineering and risks associated. It will literally go into space at tens of thousands of miles an hour and stay there, you know, around that speed. So, you know, like, this can go wrong in so many ways, right? So it's very nerve-wracking all the way up until the point that they say, you know, GenMat 1 deployed. And then after that, you know, it's like, all right, we can celebrate a little bit. And then it's like straight to LEOPS, right? Like, how do we manage LEOPS? So it was such an amazing and thrilling and like high impact experience, dude. It was so inspiring. I was like, this is a private individual and his company and 10,000 plus people who believed in the mission. In just 20 years, this is what they've done. Like, I'm literally watching a freaking skyscraper go into space and come back right now. Like, what? It was amazing. So, yeah.
That's awesome. And can you say anything about how it's going? Like, you know, how you guys did through LEOP is launch and early operations phase. So, like, how did LEOP go, and how's the satellite doing?
Absolutely. So we're currently at the very final end of LEOP, where we're working with the ADCS and GPS. So once those guys are stabilized, so the ADCS is the Attitude Determination Control System, which you know, but just in case for your audience, it helps you determine the attitude of the craft, so stabilizes it.
Attitude meaning how it's pointing, basically.
Bingo, exactly. And so we're currently just operating and fiddling around with that, if you will. And at that point, we're going to be able to start taking our first pictures. So really, really excited to get that going.
That's so exciting. Oh, my gosh. I remember. So we actually, Astronis launched a demo satellite before we did our big one. We took a picture of San Francisco from our little tiny satellite. And when that came back down, it's like, that picture is iconic in Astronis history, just because it's like that came from a thing that we built that's up there in the sky. It's an unbelievable feeling.
It feels so cool, right? It's like, yeah, felt amazing.
Yeah, you're about to, you're going to be there, man. Unless you've secretly already captured some demo images and downlinked them, but I won't press you to see if that's true. So so basically, you are probably also then developing the algorithm side too. The like actually, how do you take in all that hyperspectral data and do stuff with it, identify the deposits or whatever. So how similar is that to the other stuff you're doing? Is it a similar sort of like physics problem that you have expertise solving because you've been doing these material science things kind of, I don't know, on Earth?
Yeah, there's certainly some overlap. That's a great question, actually. There's overlap in some of the expertise. So, for example, in geological soil sampling, we filed a patent on this recently, where basically in sampling, you'll do something called XRD, X-ray diffraction, and you'll look at the crystal structures, right? You're basically taking an X-ray of the Earth, like of the surface of the Earth, like what minerals there are, and you map out their bones, aka their crystal structures, and so that is done in material science too, in high throughput synthesis and chemistry for just like new battery discovery. So that process is it's literally the same. So the models are the same as well. And then there's also sort of meta overlaps. So going back to what makes physics AI hard compared to large language models, the training data requires domain expertise. So to your point, we have a lot of domain experts in geospatial, geophysics. Our investors is, Comstock, right? They're Nevada's oldest publicly traded mining company. So we work with real world geologists too, to like validate our models. And that helps. And then, we also innovate on the algorithm side too. So how do you make useful predictions? And because we worked on, doing these physics imposed constraints and symmetry constraints and learning the nuances with material science, a lot of those learnings quickly we were able to apply to geophysics.
Very cool. Can you give people a sense, across the material science side and this side, can you give people a sense of sort of how far along you are, like how many people are at the company and like customers and sort of like traction and figuring out these things actually and being able to make them useful? I imagine that people are probably like, okay, cool, sounds like a cool idea, but like that'll never happen, but it's happening. So
I love it. Absolutely. So, we're $15 million in 40 people in 3 years worth of like results and work. So, we have preprints on the LK99. We simulated it. We have preprints on our own materials, the titanium dioxide nanoparticles, where, we've shown that you can actually use AI to dream up these new configurations and chemical surface reactions. We put up and built a wet lab. It's probably, one of the most advanced photoreactor combined with machine learning workflows in the world right now, where we have a photoreactor in Toronto. That's where we're literally creating, natural gas, right, from thin air, essentially. So we have that going for us. We also, of course, have the satellite, as we mentioned. And we also have traction both on the technology and customer side. That includes, for example, we've now been able to generate, tens of thousands of crystal structures across a wide base of material families that are all potentially trillion-dollar markets. What we want to do is continue to validate that with actual industry experts, right, in those fields. So won't be able to say names, but we've attracted the attention of pretty much every brand name you can think of, like as crazy of a statement as that sounds. So we have that kind of traction that's like really interested in adopting our stuff. And then on the geophysics side, I'm really excited as well because we were able to recently pre-train. It was a transformer-based architecture that we completely hacked to include constraints that we cared about to predict hydrothermal alterations. So an alteration is a part of the ground where the chemical composition randomly changes. Like it just changes on you. And again, this is something you may not visually see, right? But it's like very subtle but very powerful. And so how do you teach a pre-trained model to predict that on low-res Landsat data, which is like 30-meter resolution per pixel, as opposed to 5 meters, which is what the GenMat one has. So we were able to predict alterations, hydrothermal alterations, on the Comstock, and that was validated by their own geologists. It blew their mind. And this was done using a model that we pre-trained on like much worse, lower resolution data. It's not even using our existing satellite data yet. So that's another thing I'm excited to look at.
Totally. And what does this look like at the limit? Like, let's say it works perfectly. Like everything you have planned comes to pass. Where are we? Where are you and where is the world like 20, 50 years from now?
I want to bring us towards a world that I call Yug-Cyberia. So you probably see that on my Twitter a lot, like it's in my handle, right? I still have to write like a proper blog post describing what it is, to be fair. So this is a good like preview of the post. So Yug-Cyberia is the third level of civilization that I think we're headed to And I'll kind of give a brief guess as to timelines, right? Don't hold me to them. I may be way off one way or another, right? Like, don't even know anymore what AGI, like, this obscure horizon, right? Like, just warps anything, any predictions about the future. But that being said, though, you know, for us, it's like, all right, where does physics-based AI take us in the infinite first? And the first level of civilization is one where I think we will exist in a world where humans are constantly creating matter that was assisted by an AI. So every piece of matter we ever create was partially dreamt by an AI under our guidance. So we'll have these beautiful, crazy, futuristic maglev train systems, right? Consumer electronics that you don't have to charge for centuries. All these things will be the desires of a human, but serviced to us by an AI, and just optimizing the atoms, making it more sustainable, right? So just solving all the things that we currently suck at, because we don't have like chemical, quantum mechanical intuition, frankly. You have to build it over years and years and years. But if you can teach an AI that from the get-go, right, totally different story. So the first like level is one where, you know, you have hypersonic maglev trains, like you mentioned, megalithic structures. But then the second level, I think where we're headed, is where the matter itself becomes so sophisticated that it in itself becomes low levels of intelligence. So what does that look like? Well, that looks like me running straight at the wall, right? And the wall folds in on itself. So that, because it was programmed to keep humans and life forms safe. So like, I'll just like safely walk through it, right? So my wall right now is stupid. It's an inanimate piece of object, just inanimate matter. So I think matter itself will just become more animated and intelligent. Arguably, some people might, you know, start like a low-level sentience, like belief system, right? Like this should be treated as life potentially. Don't know. And then the third level is what's called Yug-Cyberia, and so that's the point at which we merge with this intelligent matter while keeping our humanity and singularity. So basically, this is a world where you can go outside and telepathically hail, right, like a flying cab. Or if your limb falls off, right, the ground will grow a limb for you. This is a world where you control matter as easy as you control thought. And I think that's where we're headed.
Hell yeah. Why Yug-Cyberia? What's the name mean?
So, fair enough. So Yug is short for Yuga, which is Sanskrit for age of. And you know, these ages are typically measured in the tens of thousands of years, right? So I think that, like, if we properly unlock physics-based AI, we'll have tens of thousands of years of innovation minimum ahead of us. And then Cyberia is just short for age of cyber, so like cybernetic matter. So in total, it's the age of cybernetic matter. So matter itself becomes cybernetic, and we control it.
Okay, awesome. So it's like we start off and we are just in a kind of our normal world, but things are better. The second world is my wall can now deform around me and like knows what I'm coming. And then the third one is like my wall's my friend. So in that world, like, which of those categories are we like on Mars and like, you know, living, like, you know, doing interstellar travel and those sorts of things? I know this is actually something you care about, is like getting beyond Earth. So when do you think it's going to happen, and how are we going to do it?
Deeply. I actually think we just need to get to the first level, even halfway to the first level, and we're already on Mars. Like, what I'm talking about unlocks interstellar capabilities, right? Like the ability to potentially hack the speed of light, if you will, travel faster than light, hack physics. By hack physics, I just mean find new physics that we didn't know about before. So Mars seems within reach, even if we go far enough along the tech tree. Because think about it, if we can accelerate the high throughput discovery of materials that reduce the cost and the weight and improves the strength and all these other, right, thermodynamic properties of the rockets, if we can accelerate that, that's just like, that doesn't require, you know, AGPI. That does not require a complete understanding of every domain of physics out there. So I'm willing to bet we're actually a lot closer if we look at that scale to Mars. And so, like, another way to look at you know, what we're kind of doing here is building the foundational civilizational technologies that are needed to kickstart any civilization. Because take the satellites, for example. If we go to Mars today, one of the first things that we're going to struggle with is, where are all the precious metals and minerals? Where are all the economically viable, more importantly, minerals that we can get to? That is a huge open-ended question that has many theoretical answers,
but nothing, really solid. So you'll want sensors all around the planet that have physics-based AI making sense of that geophysical data. So you're reducing time and resources that you need to deploy to explore and extract those resources. And then now you have a bunch of minerals on Mars. Woohoo, congratulations. Deposits that you don't have to worry about getting sued, right? By the government, the local Martian government, hopefully. Hey, we stake claims there, you're not allowed, So assuming that's not a problem, right? And you get those deposits. The next thing you're going to be asking is how do you use those raw materials and convert them into advanced materials to build colonies, to build fully functioning nuclear reactors that power a Mars base. All those things are now material science and applied physics-based problems. And so, I think Mars will get there, probably halfway to the first level of civilization. And somewhere between first and, let's say, second, we will have enough dominance of matter and understanding that we may be able to explore, creating and altering gravitational fields and all these other really sci-fi modes of propulsion may be in reach.
That's awesome, man. I can't think of a better way to just conclude it than there. We're going to be in the stars with talking in friendly walls. And no, thank you so much, man, for coming. This is awesome. I think people appreciated the wide-ranging conversation, but it always came back to first principles, which is kind of how your brain works. So thank you so much for being on the show.
Thank you so much, Christian. It's been a pleasure and honor. So much fun. Appreciate it.